Okay, so what we have here is the titration curve of a weak base with a strong acid, page 101. And I would like you to very quickly list all the, actually, could you draw on what a strong base versus weak acid would look like? No, don't do that. Ms. Spence is stupid. Just ignore me. What I would like you to do is we're going to go through and answer these questions. So here's our weak base plus strong acid. What would the initial pH be if the base in the flask were 0.1 molar NaOH instead of the weak base? So what's going to be the initial pH if we're starting with 0.1 molar NaOH instead of the weak base? That's a random stab in the dark, isn't it?
I mean, oh wait, no, not weak base.
So we have a weak base here. We have a weak base here. What if we had 0.1 molar NaOH instead of 0.1 molar NH3?
It will be 1.
Ah, will it?
1.00.
1.00. You're on the right track. So the concentration of OH is how much?
0.1 molar.
0.1 molar, which is the same as 10 to the -1. So what is the POH?
1.
1. So what is the pH?
13.
13. Okay, so obviously, if we have a stronger base, it will be at a higher pH. So why is the initial pH of the NH3 lower than the initial pH of the NaOH? Because NaOH is a other way around? Strong base, yes.
Oh, yeah.
Therefore, the pH is higher. And NH3 is a weak base. Therefore, the pH is lower. Write the reaction representing the neutralization of NH3 by HCl. Can you do it? Can you do it? Yes, you can. Bob the Builder. You guys might be too young for that. Do you guys know Bob the Builder?
Yes, I do the Bob the Builder.
Okay. NH4 plus and Cl minus. So remember, we are at the equivalence point. What do you need to ask yourself when you get to the equivalence point? When you get to the equivalence point, you need to look at the salt. So who is the salt? Actually, it's the combo, NH4 Cl, which we're just going to split apart again because, you know, when you look at it and you say, how do they hydrolyze, you have to split the ions apart. So we have NH4 plus and we have Cl minus. Do those ions hydrolyze?
NH4 does.
Yes, and Cl minus?
Yeah.
Does not. So let's write the hydrolysis equation and state whether the resulting solution is acidic, basic, or neutral. So, is our solution acidic, basic, or neutral?
Our solution is
Acidic because we made hydronium. So if we go back to our titration curve and we look at our equivalence point, what do we notice about the equivalence point? The pH is lower than 7. The pH is less than 7. And that's because our weak base turns into a weak acid, which hydrolyzes. To produce H3O plus. Is good? Okay. Could you draw what a strong base, strong acid titration would look like on this graph? How would it compare? Think to yourself, where would it start? We don't have 0.1 molar NH3 anymore. We have 0.1 molar strong base. What's a good strong base? NaOH. Yeah. Mm-hmm. What pH would we start at? Would we start at 14? Oh. We already did our calculation, right? Because what if we had 0.1 molar NaOH instead of 0.1 molar NH3, right? Okay. Something like that? Does that look okay? Ish? You look skeptical, Dorsa. What's bothering you? Is it okay? Yeah? I maybe made this go up a little bit too high. Halfway through that, but oh no, halfway is about pH 7. Yeah? Okay, so that would be our strong acid, weak base. And I know we listed these yesterday for weak versus strong for acid. Why don't you tell me the differences? Actually, tell your partner the differences between these two curves that could tell you the difference between them. What are 4 things? Differences. We got the hill or lack thereof. What else?
The vertical section.
The height of the length of the vertical section. Yeah.
For the strong acid, strong base, equivalence 27.
Yeah. The pH at the equivalence point is different. And the 4th one?
The pH is higher.
Yeah, the initial pH is different. Okay. So you have hill versus no hill. The length of the vertical section is different. The pH at the equivalence point is different. The initial pH is different. Excellent. And I don't know why I have the answer key in the middle of the book here. I have to fix that. Anyway, you guys did exercise 1 and 3. Let's do exercise 2 right now. Fill in the blanks with the correct symbol. The pH at the equivalence point for a strong acid, strong base, weak acid, strong base, and strong acid, weak base. 5, 4, 3, 2, go. Page 103, number 2. No, that's okay. We'll just wait a minute for everybody to be done. Okay, the pH at the equivalence point for strong is always equal to 7. For a weak acid strong base, it is always greater than 7. And for a strong acid weak base, it is always lower than 7. And that is because what kind of a salt do we get from a strong acid strong base? What's the product? It is a what kind of a salt? It is a neutral salt. Okay, so we have no hydrolysis. Now, how about for a weak acid and a strong base? What kind of salt do we get? We get a basic salt. The anion hydrolyzes. And for a strong acid, weak base, we get an acidic salt. The cation hydrolyzes. Is good? All right. Okay, we're going to skip the questions and we're going to bop ahead to choosing an indicator for an acid-base titration. So that is 5.6C on page 106. So we're back to indicators rather than a pH meter. And this is the exact titration that you guys already did this year. And if we look at these three indicators here, we have phenolphthalein, bromthymol blue, and methyl orange. What is the pH at the equivalence point for this titration? This is HCl plus NaOH. Yeah, the pH at the equivalence point is 7. Now, which of the indicators looks like it would be good for this titration? Bromthymol blue looks good, right? Mm-hmm. When we did the titration, did we use bromthymol blue?
No.
No. We used phenolphthalein, which changes not really very close to pH 7. It changes from 8.2 to 10.0. What volume of NaOH and that's what's going along the bottom here, volume of NaOH, is required to raise the pH from 7 up to 10. Because bromthymol blue changes at around 7, phenolphthalein is finished changing by about 10. Chat amongst yourselves, please. What volume of NaOH is required to raise the pH up from 7 to 10? No, that's to get it from pH 1 to pH 7.
Oh. Nothing.
Yeah, I want to know how much does it take to get it from pH 7 to pH 10?
0.
0. So, does it matter if we actually choose bromthymol blue?
No.
No, because the phenolphthalein will change color at the same volume because that vertical section is so steep. Okay? So as long as your indicator changes color within the pH range of the vertical section, it's a good choice. Okay? So we could choose methyl orange because it changes color within that range. We could choose phenolphthalein. Let's go to our data pages and see if we can find what would not be a good choice. So this is changing from about pH 3 to about pH 10. So grab your data pages. And if you don't have data pages, come and borrow one.
Methyl violet, thymo. Orange ivy. Orange ivy.
Of course. Yeah. So out of our first few on the list here, would we be able to use methyl violet?
No.
No, because it changes color before pH 3, before the start of the vertical section. So no to methyl violet. How about thymol blue?
No.
Except that what is special about thymol blue?
It changes from yellow to blue.
It changes from yellow to blue at
8 and 9.6.
8 to 9.6. So could we use thymol blue?
Yeah.
Yes, because we're looking for something in the vertical region. And remember, the vertical region goes all the way from pH 3 up to 10. Okay. Could we use orange 4?
No.
No. And then we're going to go down. Which of the ones at the top end would be poor choices?
Alizarin yellow.
Alizarin yellow is a little bit outside our range, and so is indigo carmine. Neither of those would be good choices. But for a strong titration, you can choose almost any indicator other than those few at the very end. Okay? And if we go back here, we can actually see what that looks like. Okay? We have our bromphenol blue, our bromthymol blue, our phenolphthalein. We can see that alizarin yellow is getting a bit dodgy, right? It's kind of like falling out of the range. And oh my gosh, methyl violet will change color from around about here-ish. And so that would be at pH 1. And so our volume, it would change pH at about, what is that, like 13 milliliters? Is 13 milliliters our equivalence point? No. So will methyl violet say this is the end of the reaction at when the reaction is actually ending? No. So it is a poor choice of an indicator. Okay? All right. Please define. See if you can write down what an end point is and what an equivalence point is. I miss the olden days. Back when I first started teaching, I just had cards with everybody's name on it. And I would just like, every time I asked a question, I would just pull someone's name on a card. But we're not supposed to do that anymore because it doesn't respect people's boundaries. Right? Somebody might be too scared to answer a question and they might feel terrible. Well, and the thing is, you never get over a fear if you never face the fear, right? Like never, right? Like, I got over my fear of spiders to a small degree by having a son and being like, I cannot give my son my fear of spiders. That would be a poor choice as a parent. So I was all like, oh, look, it's like Charlotte's Web. And we'd go look at the spiders. And, you know, if we had a spider inside the house, I'm like, oh, we should take that spider outside, right? And we'd get a container and all this stuff. Whereas before, I was like, spider! And I would just leave the stack of books because you never know, it might come out afterwards and I would let someone else deal with it. But I kind of got over it because I had to. So one never gets over one's fears unless one tries. At any rate, the point in a titration where the what changes what. The end point is where the
Panel and no titration.
nope. Indicator. Yep. It's the point in the titration where the indicator changes color. The equivalence point, on the other hand, is the point in a titration where all the actually, I should say are. All the reactants are used up, and there is no excess left over. Okay? Another way of saying it, if you prefer, I kind of like this way, it's where the stoichiometry of the reaction is perfectly fulfilled. We wanted a 2-to-1 ratio, we get a 2-to-1 ratio. We want a 3-to-4 ratio, we get a 3-to-4 ratio. It is the point in the titration where the stoichiometry of the reaction is perfectly fulfilled. I spelled fulfilled wrong, but that's okay. The graphs below show the titration of a weak acid with a strong base. For each of the graphs, write down the volume of NaOH required to reach the equivalence point, and then write down the volume of NaOH required to reach the end point. What's the volume required to reach the equivalence point? 50. Is it 50 for both? Both graphs? Yes. 50 milliliters, 50 milliliters. Now, in graph number 1, who is our indicator? Phenolphthalein. And it changes color at around pH 9. What volume is needed to reach the end point? 50 milliliters. Methyl red changes color from 4.2 to 6.0, so its changeover point will be around pH 5. What volume does it take to reach pH 5?
Around 35.
Around 35. So what's going to happen in that second titration is you're going to be dripping along, drippity, drippity, drip, and your indicator will change color at 35 milliliters. And you will say, oh, my titration is done. I have reached the equivalence point. And you will be wrong. Yes?
Yeah.
Because you will still be 15 milliliters away from the equivalence point. So if you are doing a weak acid, strong base titration, you cannot use methyl orange. Okay, it is useless to you. You could use it for strong, because the strong has a longer vertical section. Okay, but not for this one. So when we say, is this an appropriate indicator for a strong base, weak acid? The answer is no. You will reach the end point before the reaction is complete. How about phenolphthalein?
Yes.
Yes, it is an appropriate indicator. You will reach, it will turn color at the equivalence point. Is good? Okay. Okay. There are some exercises, which I'm going to assign to you. And then we're into 5.7, which we're not going to do, but I have one thing that is not in your workbook. It's very short, though, so we're just going to do it on a separate sheet of paper. Okay? What is a standard? So if you need some paper, grab some paper. If you want to write it on the cover of your book, or I don't know, last page. Yeah. Okay. What is a standard solution?
Is it the analyte? No, it's a titrant.
It is the titrant, but in a more general sense, it is a solution of known concentration. You can make a standard solution from scratch. As long as your solid is pure. As long as the solid you measure out is pure. So let's take a look at two substances. H2, C2O4 dot 2H2O. This is oxalic acid dihydrate. Could you guys please calculate the molar mass of that substance for me? 18 times 2.
Two plus
Hmm? 126? I got 126, but I could be wrong.
no 126.
You got 126? I also got 126. We're going to go with 126. 126 grams per mole. Okay, our other substance that we're going to look at is sodium hydroxide, NaOH. Sodium hydroxide. What's the molar mass of sodium hydroxide?
That's 40.
40 grams per mole. Now, let's say that I have a flask that's shaped like this. Do you guys know the name of that kind of flask? That is like the most terrible drawing ever.
I don't know what that means. Oh, sorry.
This is what it should look like. I know my drawing is like, I don't know, looks like a garlic or something.
I don't know.
Volumetric flask.
I was about to say that.
Okay, so we have a volumetric flask. And this is a 1 liter volumetric flask, just to make our math really easy. Okay. Now, oxalic acid is very pure. And it does not absorb carbon dioxide or water from the atmosphere. So if I made myself like a little pile here of solid of 126.0 grams of oxalic acid dihydrate, how much oxalic acid dihydrate do I have? I have 126 grams, which is also how much? 1 mole. And it's very pure, yes?
Yes.
Okay, very pure. Now, NaOH, on the other hand, absorbs water from the atmosphere. So you can see that we have our sodium hydroxide here. We keep it in a plastic bag.
Yes.
What are we trying to prevent by keeping it in a plastic bag?
Absorbing the water.
Absorbing water. But no matter how good a job we do, sometimes we'll wrap parafilm around the outside. Some water is still going to be absorbed. So now I'm going to measure out a pile of the sodium hydroxide. And this is 40 grams. How many moles?
1 mole.
So I've weighed out 40 grams, but remember it absorbs water from the atmosphere. Oh, how many moles? Less than 1 mole, because some of that 40 grams is water. So if I was to take my oxalic acid, 1 mole of H2C2O4.2H2O, and I was to dissolve it in there, what would the concentration of H2C2O4 be? 1. So the concentration of H2C2O4 is equal to 1 molar, 1 mole per 1 liter. This kind of substance where you can just measure it out and you're like, I know how many moles I have because whatever mass I have correlates exactly with the number of moles. That kind of a substance is what we call a primary standard, because we can just make that from scratch and we know the concentration is going to be 1 molar, okay? This pure, solid, non-absorby, that's a word that I just made up. Pure, solid, non-absorby substance is called a primary standard. We can just make it from scratch and we will know its concentration. Is sodium hydroxide a primary standard?
No.
No, because it's got stuff in it. I know that if I take this and I put it in here, what's the concentration of NaOH going to be?
Less than 1.
It's going to be something less than 1 molar, and we don't exactly know. Can you think of a way that we could find the concentration of the NaOH?
We can use an indicator and do a titration.
We could use an indicator and do a titration. What could we titrate it with?
A strong acid.
We could, but HCl is not a pure, solid, non-absorby substance.
We could use the oxalic acid and use it to titrate.
we could use the oxalic acid and we could titrate the NaOH to find its concentration. So we can use a primary standard to titrate something which we know the approximate concentration. It's about 1 molar, so we know about how much we're going to have to titrate. We need to standardize which means find the concentration of the NaOH by titrating it with a primary standard like oxalic acid. And once it has been standardized, it can be a standard solution against which you can titrate other things. Like if you needed to go titrate some vinegar, you could use your NaOH because now you know its concentration. And we are going to do a lab that is very much like that. Yay! When? I think we will start it tomorrow. So your first job is going to be to actually make the oxalic acid dihydrate solution. Yes? Yeah. Sorry, I got excited. It will be to make the oxalic acid dihydrate solution. Don't worry about the dihydrate part. The waters just dissolve in the water and you can ignore them once you've figured out the molar mass. And we'll make that solution and then we will use it next week to titrate our sodium hydroxide so that we actually know its concentration. Because I'll be honest with you, when I make the sodium hydroxide, not only do we make the original like 10 molar NaOH, right, using the impure NaOH, so we don't really know its concentration. When we dilute it, look what I'm making it in. I'm making it in a carboy that's about this big around. How precise can I be with my measurements?
Not very.
Not very. I can be like, oh, okay, I'm going to put in 1 liter of my 1 molar, and then I'll dilute, and then I'll put in 900 milliliters of water, and then I'll have, or 100 milliliters, 900 milliliters, then I'll have 1 liter of 0.1 molar, or whatever, but it's pretty imprecise. So we actually need to find the concentration of this, and then we will be able to titrate a weak acid. And we will be able to find the equivalence points, and we'll be able to find the pH at the equivalence point. And from the pH at the equivalence point, we'll be able to do some calculations and figure out what the concentration of the acid is and what the Ka of the acid is. So exciting. Yes? Okay. So that's going to happen over the next week or so. Next week is weird though, because we have like Monday is the day before your test, Tuesday is your test, Wednesday we can do stuff, Thursday is carnival, and Friday is a short-ish day. So, super fun. Okay, we'll figure out something. Okay?
Why is Friday shorter?
Well, every Friday is a little bit shorter. Every Friday. No, there's nothing special. It's not vastly shorter. It's just the classes are like a tiny bit shorter than usual. Yeah. So this has taken us to the end of acids and bases that we're going to get to because we're not going to do anhydrides and acid rain. Tomorrow, I'm going to give you a practice quiz, which you can either do tomorrow or take home over the weekend, your choice. But if it were me, I would study tonight as though I had a quiz tomorrow on titrations and buffers. So pretend that, because we don't have time to have you do a quiz, get it back to you, blah, blah, blah. So I'm going to give you a practice quiz tomorrow, and then I will give you the answer key. Okay? So pages 108 to 110 to study as though you have a quiz tomorrow. On buffers and titrations. Okay, and other than that, if you manage to find more time, you can work on the review. Is there anyone who was away last day who did not get the overall review for the unit? On the page where I've listed our test date, I've told you which questions you can omit. So if you want to, on our team, you can see you're going to omit multiple choice number 2, 40, 63, 73, 92, and written response number 7 and 11. Okay, that's in our upcoming quizzes and tests page. All right. And I'll just leave that up here for now. If you just want to go through your review and cross those questions out, you can do that right now. Okay, the rest of the class is a work block. I know there's not a lot of time, but it's at least a little bit. Okay.